Good morning, everyone. Welcome back, and welcome to our theory day. So we have part of theory, and we start actually with experimental vibes from Professor Ady Stern from Weizmann Institute. Just to tell you that in his last talk, he was telling us how we can establish new experimental scheme to measure Majoranas and topology. But in today's talk, we actually get into more to the flat band, which is the topic of our school. It will show us how we can create the most flat band. So please, Ady.
Thank you very much, and hi everyone. Good to see you again. Thanks for coming again. I'll talk about the flat band, as I had said. I'm now joining the general team of the school. And given that it's my second talk, I will overcome the temptation of showing you again the advertisement for the Weizmann course on topological quantum matter. But I hope you remember the message from last time. So what I plan today is to mostly cover two pieces of work I was involved in. One with Yarden Sheffer, who was my student, and Raquel Queiroz, whom you listened to yesterday, who was a postdoc here at Weizmann, and now, as you know, is in Colombia. And the second piece of work with Ady Stern with the Technion, and Erzberg with my colleague at Weizmann. Let me first describe what the plan is. The general idea is this. You find now the archon all over the place, everywhere, right? Every system you look at suddenly proposes to you the archon to think about or experiment with or whatever. So I'll start with the archon, and I'll look at this. I'll start with the archon and the edit perturbation with the idea of getting one of three outcomes to that perturbation. The first one, going along the path that Rafi Bistis and Ellen McDonald do to us, the first one will be to look at the ways in which the introduction of a perturbation can make the Dirac velocity vanish. So can make the Dirac cone become a flat one. So that's the first type of effect we will be looking at. In the second one, we'll go even further and ask, what can we do to a Dirac cone that will result in a band that's perfectly flat? Perfectly flat like a Landau level, if you want. And here we go along the path that was started by the Harvard group, Tarnopolsky, and the collaborators, Ashwin Vishwanath in particular, and I'll try to generalize what they did. Then a third type of outcome that can come out of such a perturbation, in which we will be interested in, is can the perturbation get the Dirac cone? Now, it's very easy to get the Dirac cone if you break the symmetry that protects. That's not going to be the case we'll be interested in. We will ask, can you get a Dirac cone keeping the symmetry that protects it and using electron-electron interaction? So this is the plan, and just as 2 days ago, you're welcome to ask questions at any point. So let's start with flattening the Dirac velocity, making the linear term in the dispersion vanish by adding a perturbation. So before we ask ourselves how to do that, let me say a few words, even though that's basically said in one way or another by every speaker in this school. Why should we do that? Why should we flatten the band? Well, the nice aspect to this is that if you take a Dirac cone that has a linear velocity, and you make the linear velocity term vanish, and in many cases that leads to a dispersion that starts as a cubic power of momentum, then you change the density of states at the Dirac point from 0 in the Dirac cone case to infinity in the case where the velocity vanishes. That's quite a sharp change from 0 to infinity. And you see, density goes like k to the power alpha, the density of state goes like e to the power 2 minus alpha over alpha, and if alpha is larger than 2, you get a divergence. Once you have a divergence at the Chern-neutrality point, you know, the sky is the limit. Many things can happen, and many of them do happen in magic angle twisted bidirectional field, for example. So this is the motivation. And there will be more motivations along the way. How can we do that? How can we make the arc velocity better? So, you know, we know one example very well. You twist two graphene layers with respect to one another, and if you play correctly with the parameter of the twist angle, you will get vanishing the arc velocity. This is the basis of McDonald observation. More generally, you know, close to the arc point, we have two states, right? For every k, we have two states. And therefore, it's a two-dimensional Hilbert space, and the Hamiltonian it has the general form of Vx kx plus Vy ky plus higher order. Now, Vx and Vy are operators working in the subspace of two states that we have per each momentum. So they are 2 by 2 matrices. So, you know, 2 by 2 matrices, which are emission, there are 4 of them, sigma 0, sigma 1, sigma 2, and sigma 3. And we can, in the most general way, write the x component of the velocity as chi 0, chi frozen, because it's similar to x. Chi 0, sigma 0, chi 1, sigma 1, chi 2, sigma 2, chi 3, sigma 3. The y component of the velocity we can again write as a superposition of sigma 0, 1, 2, and 3. And if you ask yourself what this letter is, it is the Greek letter upsilon, which is the Greek version of y. So I learned. So you see, we have 8 parameters that we want to set to 0. Chi 0 to chi 3, upsilon 0 to upsilon 3. 8 parameters we want to, or 8 functions we want to set to 0 by varying parameters. Now, if you don't want to play with 8 parameters and make sure that each one of them becomes 0. So we need tools to do that. And there are 2 types of tools: the symmetries of the system and the parameters like the twist angle. Now, there's a profound difference between the way symmetries make some of the terms vanish and the way parameters make them. And the difference is, if there's a symmetry, the system takes care to implement. If you need to change a parameter, the experimentalist needs to change the parameter. That's a big difference. And since I have more friends among experimentalists than I have among systems, I'd like to have as many of these functions, 8 functions, as many of them vanish as possible because of symmetries, so that we are left with as few as we can through tuning in the lab. So let's see how this is done, and let's start with focusing on the case of bidirectional field and look at what symmetries this system has. So, you know, the symmetries are the usual suspects. Let's start with standard versus symmetry. Standard versus symmetry in a twisted bidirectional field maps one Dirac cone to another, and we would like to make the arc velocity of a single cone vanish. So time versus symmetry by itself is not useful to us. But if you multiply it by C2, by pi rotation around the z-axis, you get what's known as C2D symmetry, which is anti-unitary, and which commutes with Hamiltonian, and which is local in momentum, leaves you in the same Dirac cone that you started at. Now, if you have such a symmetry, and this is bidirectional field does have it, then it forbids 2 of the 8 functions or operators, parts of the operators of the velocity. So you see the sigma 3, the x3, sigma 3, and the upsilon 3, sigma 3 are not compatible with the C2 symmetry, and they are out. Second set of symmetries are crystalline symmetries. And of course, in a twisted bidirectional field, we have a C3 symmetry. Now the Hamiltonian is, as we wrote it before, the velocity dotted into the momentum. Under C3 rotation, the momentum rotates, of course, and the velocity should also rotate in such a way that the product stays unchanged. And for that, you need to make you need to apply a rotation operator to the velocity operators. That rotation operator turns out is the exponent of 2 pi I sigma 3 over 3. And it has two effects. First, it forbids the zero term, the chi zero and epsilon zero. They are not compatible with this symmetry. And second, they relate the x and y components of the velocity. And that leads us to, just by these two symmetries, we arrive to the x component of the velocity being chi1 sigma 1 plus chi2 sigma 2, and the y component being chi2 sigma 1 minus chi1 sigma 2. So you see, we still have two, just finish the sentence and I'll take your question. We still have two functions that we need either to find a symmetry that will at least eliminate one of them, or to help to tune two parameters. Yes.
Excuse me, sir. I do want to ask a little bit about the C2 symmetry that you mentioned previously.
So again, we have to keep the dance match. I don't hear you well.
Sir, can you hear me? Hello?
No, I can.
Yeah, thank you, sir. Sir, can you please go back to the slide where you talk about the C2 symmetry? So originally we had a time reversal symmetry, but we see that time reversal symmetry is not enough, and we need to introduce the C2 symmetry. So where does this C2 symmetry come from, and what is the physical implication or implementation of this C2 symmetry?
The C2 symmetry is just crystallized, right? It's if you rotate the hexagon by pi rotation, you come back to the same Hamiltonian.
So it's just it is just a rotation operator because of the fact that graphene is a hexagon.
Yeah, exactly.
Wonderful. Thank you so much.
So we still have two functions, and we need to we'd like to make them both vanish. If you want the velocity, the linear term to the momentum to vanish. And now, okay, either we find another symmetry or we have two parameters. So what you see here are the two cases. Because now what's going to happen is this. We're going to play with a parameter in the system. For example, the twist angle. For twisted bilateral graphene, that's the most natural parameter, the twist angle. So what you see is on the left, or on both plots, you see the two parameter plane of chi1 and chi2. And now you change one parameter. And the question is, will you hit the origin where both chi1 and chi2 are zero? If you hit the origin, that's it. We achieved what we wanted. We made the velocity vanish, the density of state field diverge, everything we wanted. But how are we going to do that? Now, on the right side, you see the case where there is a symmetry that forces chi2 to be zero. Then if you change the parameter, you're not guaranteed, but you have a good chance of hitting the origin because you're working on a line. You change one parameter and you work on a line in a one-dimensional system. If you don't have an extra symmetry, that's on the left side, then your line will be a line in the plane, and your chances of hitting the origin are much smaller. So does the twisted bilateral graphene have another symmetry? The answer is yes, it has an approximate symmetry that commutes with the velocity in the x direction and anti-commutes with the velocity in the y direction, and that forces that basically pushes twisted bilateral graphene to the right plot, not to the left plot. Now I'm not going to get into details of this symmetry. I expect that either Andre or Nicolas will or did will do or did that before. In any case, if you now play with the twist angle In the case where you take this approximate symmetry as exact, and in the case where you don't, you see the difference. In one case, what you see here on the x-axis is the parameter, on the y-axis is the Dirac velocity, absolute value, and you see if there's an extra symmetry, it's zero. If there isn't an extra symmetry, it stays finite. So that's a first example to applying this symmetry analysis to the question of can we make the Dirac velocity vanish. The second example I'd like to talk about is a different Dirac cone. As we said, there are tons of them. So a different Dirac cone, which is a Dirac cone on the surface of a 3D topological insulator. That's a question that was first introduced by Jen Cano and collaborators a year, I think last year, but maybe even the year before, not sure. We're going to look at it, but before we're going to look at it, let me tell you what's my motivation for this. We know, and I'll mention that again later on, we know that a Dirac cone on the surface of a 3D DI is a state that's protected by time reversal symmetry and by charge conservation. You violate one of those and you get the Dirac cone. But we also know that you can get the Dirac cone even without violating those two symmetries. Even in a way that's fully symmetric, you can get the Dirac cone. It's very hard to do that. It's an interaction effect. You need strong interaction for that. And if you do, so it's very hard, but the price is very nice. If you do that, you get what's known as the T-Fabian state. It's a non-abelian state of matter. And if you were here for my talk 2 days ago, you know I have an affection to non-abelian states. So strong interactions on the surface of the 3D DI have a chance of finding this non-abelian state of matter. So that's one motivation to make the interaction strong by making the Dirac velocity vanish. Beyond motivation, again, the Dirac velocity, the Dirac Hamiltonian is Vx plus Vyky. But now, in contrast to the case of twisted bialendorphine, the symmetry that protects is time reversal symmetry that's equal to -1. And so it's the spin full time reversal symmetry. And that forbids in the velocity operators forbids the existence of sigma 0. So that kills 2 of the 8 functions we had before. We still need to kill some more. Crystalline symmetry C4 turns out forbids sigma 3, and a mirror symmetry that exists in many of those topological insulators reduces the list to having just one parameter. Now, if we want to flatten the cone, again, without breaking time reversal symmetry, because if we break time reversal symmetry, then the cone will be get. Without that breaking time reversal symmetry, the only term that you can add to the sigma 1kx plus sigma 2ky, the only perturbation that's allowed is something that does not depend on spin at all. Because anything that depends on spin will be time reversal odd. So the only thing we can add is a scalar potential. So that reduces to the question of, can we just add a scalar potential on top of the surface of the 3D DI and make the velocity vanish? And the symmetry analysis tells us that we should be able to do that with one parameter only. And you know, the natural guess to start from is, let's put a periodic potential, you know, some cosine in the x direction plus cosine in the y direction, and play with the amplitude of the cosine, hoping to get the velocity to vanish. And that was actually studied thoroughly by Jen Cano and her collaborators. And that doesn't quite do the job. It reduces the velocity quite significantly, but not all the way to 0. We went a little bit further and managed to make the velocity vanish completely. You see, by the way, the potentials, it's kind of an egg carton, and you see the C4 symmetric case up there and the C2 symmetric case down there. Anyway, we found two ways to make the velocity vanish. One by breaking the C4 symmetry of the potential to C2, and the other one by having a C4 symmetric potential with some twist. You can see it written there. The details are not important. What is important for me to emphasize is that this is not really a theoretical game. This is something that can be done in a lab, I think, without tremendous efforts, well, at least from the point of view of a theory. Because what we need is to apply a periodic potential on the surface and play with the amplitude of the periodic potential. One way to think about maybe applying surface acoustic waves. They are big acoustic waves. They move pretty slowly, so you can think of them almost as static potential, and they can do the job. Now, what do I mean by doing the job? So what you see in the upper plot is this a C2 symmetric perturbation. So you see the amplitude of the potential in the x direction and the amplitude of the potential in the y direction, and the color indicates the velocity, the Dirac velocity that comes out of the application of the perturbation, and the dark blue regions are regions where the Dirac velocity vanishes. What you see in the lower plot is that the band structure that you obtain and the density of states that you obtain out of that perturbation. And you see at zero energy at the Dirac point that there is this huge peak, very sharp divergence of the density of states going like 1 over e to the power 1/3, if I remember correctly. Yes, 1 over e to the power 1/3, coming out of the vanishing of the Dirac velocity, both in the x direction and in the y direction. Okay? Now, what I told you so far was a recipe for flattening the Dirac velocity, for eliminating the linear term in the dispersion. And what I wanted to, the message was, you need to identify the most general velocity operators that are consistent with the symmetries of the problem. The symmetries are supposed to make this most general velocity operators a small subset of the full subset of possible velocity operators. And then you want to introduce a perturbation, excuse me, that you will fine-tune to get to a point where those operators vanish. Okay, then you get this diverging density of states. So that's one step along the way of making a Dirac cone narrow. But what we'd like to ask now is, how do we get perfectly flat then? So not just taking the Dirac cone on the left and making it like the one we see at the center now, making it start with a cubic term of the velocity, a cubic term in momentum, how do we make it perfectly flat for a finite range of momentum? And that's what I'd like to discuss now. But maybe let me check questions.
Yes. Oh, wow.
Hello, Professor. So one question I have regarding symmetries when you try to impose the
If you could use the microphone better.
Doing my best. Is it better?
Yeah.
Okay. Have you tried to use combination of symmetries like CP to constrain?
Like what?
Like CP, the combination. You use like separately parity, C, and time reversal. So I was like inspired by particle physics when people try to use like combination of it, like CP and other different things.
Yeah. What you saw here was one example where I needed to combine symmetries in order to have a symmetry that keeps me in the same UR form. That was the graphene. And the other example where time reversal was keeping me in the same UR form. For the first case, you must combine symmetries. Now, there are differences between the cases where you have both C2 and T, and the case where each one of them separately is broken, but the product remains. And actually, I'll show you such a case. So,
yeah, and just a general question. Like, I don't know, do people use continuous symmetries for this kind of applications, or it's just?
Okay. It's, continuous symmetries. U1 as a charge conservation plays a role. U1 as a crystalline, not crystalline, but as a something that holds an isotopic system doesn't really play a role. And I don't know, do you have any particular ones in mind?
No, I guess just, well, it depends how deep you want to go, right? So you can go to SU space, or you can go to just real dimensions like O space.
Yes.
Yeah, so because, for example, when you said you want to find the peak of the cone, my first immediate reaction, like, you could just try to find the vacuum expectation value, like, false vacuum expectation value in the sense by minimizing your potential. So in that sense, you're using the continuous symmetry, and then you can try to move left and right, or on the corners using the discrete symmetry.
Yeah.
I'm not an expert.
Yeah, it's an interesting suggestion. We didn't do that. We looked at mostly crystalline symmetries because those are the ones to encounter.
Right.
Continuous ones you have with a superconductor, and you can ask, can you play with breaking or with the superconducting phase in cases of the cones, and I don't know. It's a good question.
Right, because I usually think about the ansatz I would start, and for example, just to make it like, flat Dirac cone, you could just start with suggestions like amplitude times exponent minus some kind of function, and then you look for the amplitude, and you kind of throw in mathematical or other tools to get this shape.
You want to start with the amplitude times exponent of what?
Oh, it's just the answer for this kind of potentials. This is how, like, I've seen people doing this when they kind of try to minimize it, and you get as a solution for this amplitude is usually x to the 4, so it's like quadratic or quartic interaction, and then you get this exactly the same shape. But this is an entirely different world, so I was just wondering if people do something like that.
It's actually, it's an interesting idea. In a good world, we would discuss it over coffee right after the talk.
I'm actually looking forward to you. I'm at UCSB and I go to Caltech pretty often, so I'm happy to step and discuss one day.
You are where?
Oh, I'm saying I'm at UCSB working with Mark Tridnicki and Dirk Baumeister, so I go to Caltech pretty often, and you're from Caltech, right?
No, I'm not from Caltech. I'm from Weizmann.
I haven't switched my first office.
But if you write me, I will have my email.
I was ready, so thank you. Wait, we have another person.
Yes, so far I think you discussed the fact that the cones are linear. Is it this scenario also true when I have a quadratic, starting with the quadratic cones?
Yeah, a good question. Can we start from a quadratic dispersion and make it into higher power? Actually, we're looking at that now. I don't have anything that I can present yet, but it's something we're looking at now. How do we get perfectly flat band? Well, I'm going to address the three issues on that. First, I'm going to ask what symmetry classes allow for perfectly flat band, and you'll see what I mean by that. Second, I'm going to ask, suppose that I have a perfectly flat band and I add a magnetic field. What does it do to that perfectly flat band? And third, which we'll see how time goes, we came up with a new model for fine-tuned perfectly flat band, and if I have time, I'll present it to you. But the way this evolved was there is this work which I mentioned before of Tarnopolsky and collaborators that looked at what is known as the chiral limit of the twisted bilayer graphene and found there a fine-tuned perfectly flat band. And I presented the question to my two collaborators, is this the only one? Is the magic angle twisted bilayer graphene fully magic in the sense that it is the only flat band, possible, or can we find a recipe to generate others? And that's what I'd like to discuss. So to start with, we know flat bands in physics before this started, and there are two types of flat bands. They're not the only ones, but there are two types of flat bands which I'd like to mention because they are very different, and the difference will be appreciated. One is an atomic insulator. Basically, you take an array of atoms and you keep them very far away from one another so that the tunneling matrix element between them is zero, you get a perfectly flat band. But it's a very, let's say it's not very interesting one. It basically takes you back to atomic physics. There is no hoping. The second one that's very, very different is the case of Landau levels. Now, Landau levels, we know, exist in situations where electrons can move from one atom to the other. They move, there is a tunneling matrix element, and yet, because of the magnetic field, they form an exactly flat band. In particular, I'd like to remind you of the case of Dirac electrons, Landau levels of Dirac electrons, because basically the answer to the question I'd like to ask is hidden there. So let's talk about Dirac cones of graphene. Let's start even without them. Well, we know that Hamiltonian is K for monolayer graphene is Kx sigma x plus Ky sigma y. The velocity in the x direction is proportional to sigma x. The velocity in the y direction is proportional to sigma y. And the Hamiltonian has some symmetry. It has chiral symmetry. It only commutes with sigma z. And you notice that Vx times Vy is proportional to the chiral symmetry. It has time reversal symmetry, that's a complex conjugation times sigma y. It has particle hole symmetry, that's complex conjugation times sigma x. And chiral symmetry is, of course, the product of the two, of time reversal times particle hole. Now, the expressions for time reversal and particle hole depend on whether you look at the Dirac cone of graphene or Dirac cone of 3D surface state of a topological insulator. Those two may interchange with one another, but one thing that's important is if you square K sigma y, you get -1. If you square K sigma x, you get +1. Meaning T squared and P squared have opposite signs. Okay, that's going to be important. Those are two anti-unitary symmetries. One commutes with the Hamiltonian, the other one anti-commutes with the Hamiltonian, and they square to opposite numbers. Now let's say the magnetic field. So the Hamiltonian changes instead of Kx sigma x and Ky sigma y, we have Kx minus Eax. We add the vector potential. The vector potential is related to the magnetic field in the usual way. And just for your convenience, I write Hamiltonian also in a matrix form. Now let's look again at the symmetries. So chiral symmetry is still there. The Hamiltonian anti-commutes with sigma z. Time reversal symmetry is not there anymore. You put the magnetic field. Of course, there's no time versus symmetry. Particle Hall symmetry is also broken because if you have chiral and you don't have time reversal, then you don't have particle Hall. Which we can say is p squared is 0 and p squared is 0, meaning those symmetries do not exist. So again, p squared and p squared are negative of one another, even though it's less significant here. So that's a 3 minutes review of the physics of Dirac electrons in a magnetic field. Now, what we'd like to do now is to combine the Landau level spirit, what I call. Excuse me for a second. Thanks, sorry. So we'd like to combine the Landau level spirit, namely the general shape of the Hamiltonian, but we'd like to have not a Landau level because of the magnetic field. We'd like to have flat bands which are time reversal symmetric. So we'd like, so of course we need to have two flat bands which are time reverse partners of one another, and which will be, as it turns out, degenerate with one another. So we need a bigger Hamiltonian because we need twice as many states per each momentum as we had before. So instead of this Hamiltonian that we had in the earlier slide for electrons in a magnetic field, what we're going to do is we're going to replace this upper right term, kx minus eax minus iky minus eay, which is the term that you have in the Hamiltonian of electrons in a magnetic field. We are going to replace the vector potential by a 2x2 vector potential, which is to say we are going to replace the electromagnetic gauge field that gave rise to the magnetic field by a non-abelian gauge field, namely a matrix of 2x2, a non-abelian gauge field that will be time reversal symmetric and that will lead to the same exactly flat band structure that the Landau level has. Okay, now driven by the observation of the Landau level, we're going to keep looking at the case of t squared equals minus p squared. Either t squared equals plus 1 and t squared equals minus 1, or the other way around, or both of them being 0. Okay, now once you define whether you have or do not have time reversal symmetry, whether you have or do not have particle Hall symmetry, and what is the square, you identify yourself with one of the 10 Altan-Sternbauer classes. And here, or Cartan classes. And here you have on the slide those 10 classes. And only 3 of them satisfy p squared equals minus p squared and having a chiral symmetry. In fact, only 5 have chiral symmetry. They are the corners, P2, P3, but the other gray one have chiral symmetry, and only those which are encircled by ellipses have t squared equals minus p squared. So those 3 are the candidates to look at, and that's where we look to find models with a perfectly flat band. As it turns out, these 3 doesn't work, and the other 2 do, C1 and A3. Now, A3 is going to be the flat band when there is a magnetic field. C1 is a case where you have a perfectly flat band with with time reversal symmetry, with no breaking of time reversal. Now, one remarkable aspect, which I'm not going to get into the details of, that comes out of this analysis, is that in those classes in which you can have a perfectly flat band, the way to find this perfectly flat band is to do the analysis from which we started, namely to look for a vanishing of the Dirac velocity. Because if the Dirac velocity vanishes, the band becomes flat. The band becomes exactly flat. There is no distinction between those conditions. In other classes, there will be a distinction, and you can make the Dirac velocity vanish, and yet get the band that has dispersion, like k cubed or k to the fifth power or whatever. In those two classes, C1 and A3, if you make the Dirac velocity vanish, the band is perfectly flat. That's one thing that comes out of this analysis. Another thing that comes from this analysis is this. Once you suppose that you find the perfectly flat band and you analyze it, you look at its properties, you try to understand it. What you find, or what we found to our surprise, maybe excuse me, it may be in hindsight expected, but I didn't expect it. What we found was that those two flat bands were basically Landau level. In what way? You can write the wave functions of those bands. You know, they are bands, they are block bands. So in principle, you can write the wave function as block states with a given well-defined momentum. You can, but you don't have to, because it's a flat band. All states are degenerate. You can also take linear superpositions of states with different values of the momentum. And if you do that, you find that you can span these bands with a Landau level wave function, so with something that looks very much like Landau level wave function. I'll finish this and I'll let you ask. In what way does it look like Landau level wave functions? Well, how do Landau level wave functions look like? How do they look? When I say Landau level, I mean the lowest. The lowest Landau level is a polynomial in C, multiplied by a Gaussian factor that's e to the minus z actual value squared over 4 times the magnetic length squared. And they are sublattice polarized. So either sigma z equals +1 or sigma z equals -1. That's the lowest Landau level in grouping. Now, the place in that wave function where you find what is the magnetic field is the Gaussian. Because you see the magnetic length is there. So that's where where it's imprinted, what's the magnetic field that creates this Landau. In the perfectly flat band that you find in the procedure that I described to you, the wave function looks like a polynomial in Z, same thing, Gaussian, same thing, another factor G of R, which is periodic or quasi-periodic, periodic up to a phase on the lattice that the perturbation creates. But the crucial point is, if you look at the Gaussian factor, what you see that it tells you what is the effective magnetic field, and the effective magnetic field is 1 flux quantum per unit cell. So the two perfectly flat bands that you find, one describes electrons in a magnetic field with 1 flux quantum per unit cell pointing up, and the other one has electrons in a magnetic field with 1 flux quantum per unit cell pointing down. Okay? Now I promised someone there. Yeah.
Hi, thank you, Professor. Sorry for the lots of questions. Based on our previous discussion, we have a priori assumed that our wave function looks like this polynomial multiplied by the Gaussian times a spin component. So I was just wondering, where is the physical origin of the Gaussian term, like the exponent of -z squared over 4 LB squared? Where did this term come from?
Okay. We can ask where does it come from? First, let's ask for electrons in a magnetic field, where do we get the Gaussian from? But first, let me ask you a different question, which is, if I write on the board, do you see?
Try.
I don't know what you see on the board. Do you see my presentation or do you see myself?
Yeah, we see the presentation, but you want to try if you can write.
No. Then if you don't see me, if you don't see me, let me use this and explain what I want to say.
Thank you.
Using my presentation. So let's look at the upper matrix. Okay, now you know kx minus iky. This is if we write it in terms of derivatives, this is a derivative with respect to z bar.
Yes.
And the rest is some function in principle of z and z bar. Now, first of all, since we have a derivative with respect to z bar, that tells us that any function that's a function of z solves this, will give us a zero eigenvalue of this equation.
I think we can see you now. If you want to write on the board, we can see you now.
I can write.
Yeah. We fix it. Yeah, you can.
Okay, so let's see if the pen runs. Okay, good. So what I like to say, I'm not going to be careful about the factors of I, 2, minus, plus.
Yeah, of course.
But what I'm saying is, in the Hamiltonian of graphene, of a graphene magnetic field, we have this term here, and we have this term here. Let's look at this one. This one has d with respect to z bar, and then some a of z and z bar. Okay, now you see that tells us that if any function that I write that's a function only of z will be an eigenvalue of this operator with will be an eigenvector of this operator with an eigenvalue of 0. Right? So in principle, I could have written any f of z. But of course, I cannot. This is not a culture eigenvector because it's not normalizable. So this is why I need a Gaussian. I need something that will make this decay at infinity. I assume you see what I write?
Yes.
Okay. So this is why we need this. And in fact, we need just one eigenvector of this type, and then we multiply it by any polynomial of z, and we have an entire set of them. Now, in the case of electrons in a magnetic field, this is 1/2 b times z, right? And that gives the Gaussian, because either z or z bar is, I think z, right? Yes. So now if you substitute the Gaussian into this, you see that this operator will annihilate the Gaussian. So what we need is to get something that is analogous, that plays the same role as the Gaussian, but to get it from the non-abelian vector potential that you see. I hope that you also see the presentation.
Yes, Professor, we see the non-abelian vector potential as matrix. Yes.
So okay, so in some sense, the question of how do we get the perfectly flat band becomes a question of how do we solve this lower equation with the non-abelian vector potential in a way with a solution that decays at infinity. Now I don't have a general answer to this. One thing that makes it easier to answer is the fact that I mentioned before, that if you make the velocity vanish, this will take care of itself.
So we just say that
Okay.
so basically our argument is because of the addition of the Gaussian factor works, so it's the only thing that works, so we're going to assume that this is correct. Is that?
You can show it on a case-by-case basis, but yeah, that's the one.
Oh, so thank you, Professor. Sorry.
Okay. So the point that I stop that was we have two perfectly flat Chern bands, one corresponding to electrons in a magnetic field pointing up, one corresponding to electrons in a magnetic field pointing down. And of course, they have the same number of states. Now, what's going to happen if we add a magnetic field, a real, honest to God magnetic field in the lab? Then, you know, in terms of the Hamiltonian we now have also extra terms in the diagonal, which are the same in the two elements of the diagonal, because it's the same magnetic field for the two bands. But what will it do? Well, it turns out it doesn't. The crucial point is the bands do not acquire a width; they stay perfectly flat. So the two bands, one with a magnetic field up, the other one with magnetic field down, stay perfectly flat. But what changes is the number of states each one of them has. So, you know, the one with the magnetic field, if the external magnetic field points up, then for the band that was effectively feeling a magnetic field pointing up, the magnetic field goes. While for the other band, it decreases. So one band becomes more degenerate, there are more states into it, and the other one becomes less degenerate, there are less states. This is an observation, that's not the first place where you see it, but it's an observation that is kind of disturbing. You know, we learn, if there's one thing we learn in solid state one, it is that each band, the number of states in each band is the number of unit cells in the lattice. And here it's not the case. Here the number of states in one band and in the other band are not the same, and they change with magnetic field. Which actually has another consequence that's really very nice. So you know, let's ask ourselves, at zero magnetic field, what's the Chern number of those two bands together? So of course it will be zero. At zero magnetic field, the Chern number, you know, it's a time versus kinetic system. So the total Chern number will be zero. Moreover, if I put a small magnetic field, I have two bands, one richer, one poorer, one with more states, one with less states, but one has Chern number 1, the other one has Chern number -1, altogether the Chern number of 0. Now I turn on the magnetic field, I make it stronger and stronger. The rich get richer, the poor get poorer, no politics intended. But that's what happens. Until at some point, the band that was losing states all the time has no more states to lose. Because, you know, the number of states in a band is a positive number. At some point, this band is just eliminated. And now you have just one band with Chern number of 1. So the total Chern number changes from 0 to 1 as you change the magnetic field. But if there's one sacred thing in this business, it is that Chern numbers do not change with the gap, without the closure of the gap. Which means, and you see that in the plot here, which means that as you turn on the magnetic field, and all our attention in the last 20 minutes was on the perfectly flat band at zero energy. When you turn on the magnetic field, there is no choice. Without any calculation, we get to the conclusion that by the time you fully empty one of the two bands, the bands from above and below must close. The gap must close. They must come and close the gap in such a way that the Chern number can change. Okay? So this is I like this conclusion because it involves no, you know, you see it happening in the numerical calculation that is here, but you don't really need it. Okay, you could get to the same kind of conclusion without numerics. Now, my understanding, I have it told me from home, is that I have like 10 minutes.
That's okay.
If you don't have a watch, don't do. Don't really take mine. So I think what I'll do is I won't show you. So we derived another model based on two 3D DR cones put on top of one another, as this clumsy figure shows. And we couple the two DR cones of those surfaces to one another in such a way that creates a perfectly flat band. But I don't think I'll go into the details because I'd like to tell you also something else. Okay, so you remember when we started the talk, I said we start from the DR cone. We can either make it velocity varying, or make it into a perfectly flat band, or get. So let's look at the situation of getting. So basically, let's say we started from a DR cone. We flattened it completely into a perfectly flat band, and now we shift slightly away from the magic value of the parameter. So what are we going to have? We are not going to have now perfectly flat band with Chern number +1 and perfectly flat band with Chern number -1, as we had just 2 slides ago. Instead, what we're going to have is a not perfectly flat band, but some bands with some, width. One with Chern +1, one with Chern -1, and with coupling between them. And the coupling is going to be a coupling, or the coupling we're going to look at is a coupling that keeps C to T, keeps the C to T symmetry. And we're going to ask, can this structure be get without breaking any symmetry? And the answer is going to be yes. This is put in different terms, which I didn't discuss in depth. Those two Chern bands with opposite Chern numbers coupled to one another with a C2 symmetric coupling. This is what's known as a fragile topology system. So basically what I'm going to tell you is that a fragile topological or band with fragile topology can be or the fragile nature of the topology is going to be manifest by the effect of electron-electron interaction. So let's look at the simplest model where we have Chern +1 and Chern -1 coupled to one another at the same energy. So I'm going to do this. I'm going to take a pair of Chern bands, the brown one of C equals +1 and -1, another pair of Chern bands of C equals -1 and +1. You see the y-axis here is the energy. So at low energies, we have just one band of C equals -1, another band of C equals +1, and we're going to couple them in a way that's C2T symmetric. But before coupling them, let me quickly say a few words about what a Chern band is. I kind of suspect that one of the other speakers already discussed this, but I'll do it fast. First, what is a Chern band? It's a band that carries a quantized Hall conductivity, right? Either plus or minus some integer times the square of area. And we looked at the case of C equals +1 and -. Since we have two bands for each of these, for each of these two sides, the brown and the green, we have two bands. For each of those two, the wave function is a two-component spin-o. And for the band to be a Chern band, the spin-o, as you vary momentum, must cover the entire block spin. This is a necessary condition for a band to be a Chern band. And the next property that I'd like to mention is that there's no gate choice in which the wave function is moved. There must be a point in momentum space around which there's a winding of the phase of the spin-o. Now we're going to, as we said before, now we're going to couple two Chern bands of opposite Chern number, and you see I'm not even drawing anymore the bands above the chemical potential. not going to, particular that I have 5 minutes, they're not going to be part of my discussion. Now, we want to couple those two in a way that keeps C to T symmetry, and I call it here C to T plus, just to remind you that this is a time reversal that's equal to plus, not speed full time. If you, by the way, if you couple two such states in a coupling that's symmetric to T minus, you would find a 2D topological instance. We're interested in something else. So this symmetry C to T plus being anti-unitary symmetry that's equal to plus 1, in the Hamiltonian, if I write a low energy Hamiltonian in terms of a 2x2 matrix that combines the two bands, not each band with its partner of high energy, but the two low energy bands, and I call the set of matrices eta 0, eta x, eta y, eta z. The symmetry will forbid me from having eta y, meaning it will force me to have a real Hamiltonian. And in particular, in such a situation, if I have a Dirac point in the band that in the coupled system that I form, if I have a Dirac point, I cannot get it because it's symmetry protected. Because the way to get it is to introduce a master, but one of the Pauli matrices eta y in this case is forbidden, so I cannot put in a master. So once I have a Dirac point, it's protected by symmetry. But do I have a Dirac point? The answer is yes, I have to have one. And the reason is this. Think about the Hamiltonian written in the way that I write it here. It's H2 times sigma 3 for eta z and H1 times eta x. Okay, now, so H1 and H2 are real. So think of them as two-dimensional vector. On the plane, K is not the plane, it's the torus. But think of for each point of the torus, you have a two-dimensional vector. Now you can ask, does this vector wind as a function of K? Does it wind around some K value? Well, there are two situations where it will wind. One is when you have a Dirac point. That's the one we are used to. When you have a Dirac point, the winding of the spin-off. Another is if there is no Dirac point, but the basis vector from which you formed the Hilbert space of the two lower bands, the basis vector has a singularity by itself, which is the case here. Because you remember, we said that there must be a singularity in the band in the spin-off in order for the band to be a Chan band. There must be a singularity. So there must be points of winding coming out of the bands being Chan bands, and those must be neutralized by points of winding of a Dirac point. So this kind of coupling that's drawn here at the upper right part of the slide, this kind of coupling necessarily gives rise to Dirac points. And it's these Dirac points that we want to try and get in 3 minutes. What you see here are the two Dirac points, and what I just said is that you can, by playing with these two Dirac points, bring them closer to one another, you cannot get them. They have the same chirality. You cannot get them because they must exist for the reason I just said. But one thing you can do is you can make them into a single one with a quadratic dispersion. So you can make this into a quadratic band touching point, and that's actually what we are going to do. So I'm doing very fast because I'm in trouble in terms of time. So just say, okay, you see, we have a quadratic band touching. A quadratic band touch may be get if you bring another band. If you bring another band from outside, add another band to the system, another orbital or something, just a topologically trivial band, and bring it down to the energies where the quadratic band touching is, they can usually get, and you see it in the picture. At the lower picture, at the upper picture, you see the quadratic band touching in red, and this extra band in blue. At the lower picture, you see how the new band gets. And on the left, you see the Hamiltonian. The 2 by 2 upper left block is the quadratic band touching, and the lower right term is the trivial band. If you couple them in a particular simple to find way, you get this. So by having another band, you can get this coupled system that we created. But can you do that without having another band? This is what electron-electron interaction lets you do. That will take 2 minutes. So, you know, what we, the rules of the game are that we are allowed to play with the band structure of those 2 bands without, as much as we want, as long as we don't break any symmetry. And we're allowed to introduce any interaction we want, as long as we break no symmetry, even spontaneously. We're not talking in this work about you know, feasibility, about whether it's realized in this graphene or that PMD. It's a question of principle. Can we write an interaction that, without introducing a new band, can get this quadratic band touching point that originated from the coupling of chain bands of opposite chain numbers? The way we do that is we use the 2 bands that we have to create a third band. And we're inspired by concepts from physics of semiconductors, which are actually now very relevant to semiconducting PMPs, and that's the concept of an exciton and a trion. An exciton is a bound state of an electron in a hole. It's a boson, and it's not good for us. A trion, it's not good for us, but it's more familiar to many people, so I mentioned it. A trion is one step further. It's a bound state of 1 hole and 2 electrons. In some sense, like you know, negative hydrogen ion. It's a fermion. It has, you know, it has 2 electrons and 1 hole. It's a fermion, and it's a bound state. And if its center of mass has a momentum, it's a new degree of freedom made from the band that we have, made by interaction from the band that we have, a new degree of freedom that's fermionic, and it can do the gapping of the quadratic band touching that we wanted. And the way we create it, again, it's a matter of principle. We change the band structure in such a way that we make a trion a bound state, and we'll make the trion form a band at the small momenta, and we couple the band. Sorry for doing this so fast. We couple the band to the quadratic band touching and get the gapping that we want. So I'll just say that without details, I'll just say that in the case of twisted bilayer graphene, what this means is you can, in principle, get a gapped state, for example, a charge neutrality. You can get a gapped state without breaking of any symmetry. So you don't need to have the, you know, various intervally coherent states that are able to create gaps and create insulating states. They're not essential. You can even have a symmetric, fully symmetric gap with the Dirac-Ohm's zero, a charge neutrality being gapped. So again, I'm running over this. Sorry for that. I just summarize what I told you, that the combination of symmetries and fine-tuning of parameters opens the way of flattening of Dirac bands, not just in twisted bilayer graphene, but also in other systems. I told you how you know, one possible way to analyze the role of the symmetries. I said that perfectly flat band may be created in classes C1 and A3, and I told you the recipe how to do that. And then in the last 2 minutes, I said that fragile topology lives up to its name. A pair of fragile bands may be gapped by interaction. Or alternatively, you can say a featureless insulator may be constructed in a half-field pair of fragile bands. Thank you very much. I have to tell you before you ask a question, just so that you appreciate the experience of the other side. I hear you only if you speak to the microphone, which means the scene of the clapping is completely soundless.
We can do it again.
Okay.
Professor Stern, do you hear me?
Pick up.
Yes.
Can you hear me? Thank you. Thank you for a very interesting talk. So I hope I can ask maybe 2 or 3 short questions. No, one question.
Yes.
One question. Then and that would be, so you talk about interaction gapping gapless nodes. So maybe linear Dirac dispersion or quadratic or even higher order gapping. So do you think there's a guiding principle on what kind of interesting topological order that can appear if you get a linear dispersion or quadratic dispersion or third order, high order dispersion? Would that order of the dispersion put some constraints on what kinds of topological order that you can have if you get it by interaction?
Okay, so I assume you still see my board, right?
Yes.
You know, I said that in the context of the surface, the icon of the 3D DI. I think that the constraint to the constraint that will be imposed on the gap state that you can have. One way of understanding it is this. Imagine that you have a 3D DI. This is the surface of a 3D DI. Now I'm getting it in the following way. This is magnetized with a spin up. This is magnetized with spin down. And this is a superconductor. Now, of course, nothing sophisticated here. It's gap because you both universal symmetry or charge conservation. Now, out of that, we know there will be an edge state that will go like that and will split just by symmetry like that, so that here we're going to have a Majorana state, here we're going to have a Majorana, right? This is because this is a C equals 1 free fermion edge state, and it must split to 2. So the only way to split to 2 will be to have 2 Majorana states. Now, in place this superconductor by a symmetric state. Now, nothing changed in the argument. Nothing changed. Still, this edge state come here and must split into 2, just by symmetry. So there must be a Majorana state here and here, but now this is a Majorana state that lies on the edge of a charge conserving system. That can happen only with topological order. So that will, and that tells us not quite which topological order, but it tells us what the central charge at the edge, and hints towards the Ising kind of topological order. Now, is this going to depend on what was the spectrum when you started from? I don't think so, but maybe, but I don't know. I don't have a strong argument like this one for that. Okay.
Yeah. Thank you. We have another question.
Yes. Going back to the flattening mechanism that you introduced, I think you start with the case that system is gapless, so you have well-defined velocity for the bands, and then you flatten it. But if I start from the case which originally the system is not at all gapless, it's gapped like TMDs, right? Then is it possible to flatten it again?
So could you Repeat the second part of the question.
Yeah, the second part was that if I start with a system which is gapped, not gapless, so it doesn't have a very defined velocity in that sense. Is it,
Yes.
this recipe is kind of work?
So if you start from if you start from a gap from the very beginning from a get PR cone, that's a PR cone. If you wanted to get to any of the two states I started with talking about, the perfectly flat band or the diverging density of states, PR cone, the first thing you need to do would be to close the gap. So that would probably be the first tuned parameter to close the gap.
But that would probably change the topology if I close the gap. I don't want to change the topology of my bands.
You don't want to change
The topology of my bands, because if I close bands, it might change your topology of the bands.
Yeah. No, but then you need to define what your goal is. You'd like to, you start from a massive DR cone, and what do you want to,
I want to get that massive bands become fully flat.
I see. So basically you want to start from a quadratic dispersion
Yeah.
and make it perfectly flat.
Yes.
So, with a breaking time versus symmetry, it is just put a magnetic field. Without breaking time versus symmetry, I don't have a way in my head. I don't have an idea to do that without closing the gap.
Thank you.
We have two questions from the webinar attendees.
Okay, can you hear me?
Yeah.
Okay, the first question is the system guided by the fine tuning stable or disordered?
Depends what we call stable to disorder. We have a band, it may be perfectly flat. Now we put in disorder. The first thing we lose is the band. It's not the question whether it's perfectly flat or not. We don't have a band anymore. The spectrum will not remain uni-energetic, one energy only. There would be localized states above and below. That's the first thing that would happen.
Okay, thank you. The second question is, what is your effective edge theory? How would it be different from that of a square root of 2D Z2 spin-Hawk model?
What is the effective word?
Effective edge theory, and how it's different
Oh.
from a 2D Z2 spin-Hawk model?
No, okay. When you get couple the two diagram in this fragile way, there aren't any. If I guess correctly, Nando is the next speaker, then he's the one to explain it to you because he explained it to me.
We can say this to the next speaker. Okay, thank you so much.
Thank you very much.